So much. Hello, friends. Another session, another round of discussion, another round of learning, unlearning, and everything. So, what we do today is we would shift our session into, divide our session into two sessions, two basics. In the past few sessions, we have been typically focusing on different aspects of fecal sludge management, fecal sludge, septage we have been talking. But we often tend to forget that there is another sector of wastewater that is generated in our houses, which often gets overlooked because we don't have a tendency to give it much of an importance that it is a wastewater. And again, it could become as a used water. Rather, I would say put it in that way that it is a session where we would try to talk about some wastewater which could be treated and reused. Not only it doesn't, it involves fecal sludge, septage, obviously, but then there is the other part that is a grey water we have often spoken of. We often tend to overlook a bit. To set the context, I'll just take a few minutes from you before I call in our other speakers of the day to just let you know, give you a very brief idea of what this used water concept is, what it is, where does it come from. Okay. So having said that, I'll just pull on my slides for a few seconds. Now, talking about as our session today is on design and selection and processing of treatment technologies, especially our session today, the first part of the session, first 1 hour, we'll be talking about used water management. Now, what is this used water management? If you see the pie chart that is shown on the right-hand side of this slide, you see most of the countries, we are actually in a great, what should I say, risk of having proper water supply, water. If you see, 94% of Africa is living under living under lack of reliable water sources. Asia Pacific, 4.38 billion people live under such kind of a threat of having water resources. Now, why is this? It is because the amount of wastewater we generate, we never think of treating it. We think of treating it, of course, whether it is gray water, black water, we all have started, and especially this group has all started thinking, people are working on it. But then we don't tend to think of in a manner that after treatment, why not reuse it? So it's not just the gray water, black water, which are major sources of pollution, but then they can be treated to certain standards and reused. Now, reuse can be of different types. I'll be speaking in my further slides. It could be a domestic reuse. It could be a community-based reuse. It could be a industrial-based reuse. All these could be taken up as a reuse. And that's the reason we talk of reuse, used water management, managing the used water. Water which has been taken from a virgin source, that is from a groundwater source table or from a water resource body, and then used. Now that is we call it wastewater, we treat it, and then that can be used. We call it the used water at that point of time. Now, what is the present scenario? If you look around, this is something, of course, I took it from one of my seniors or my senior consultants who actually did these drawings, and I found them interesting, so I'm presenting it to you. So the drawings say clearly that when we look around in our houses, we see that there is a major drain flowing out, and each of our house outlet drains are connected to that major drain. And I'm sure that very many of you would agree to this situation, which you which we see it, just we look around left or right, we would see the situation in and around our places. Now, what does this does? If there is a drain, if you see my previous picture, if this is the drain I'm talking of, and then this is the same drain I'm talking on a longitudinal section I'm talking of, what happens is because this drain is flowing with dirty water is getting seeped into the ground level below. And from this ground level below, we call it the recharge point, the groundwater level getting recharged and so on and so forth. This water is again rising up to our overhead tanks. And we are ultimately, what we are using is this drain water's contaminated, recharged water into our tanks. Right? We have never thought of this. So what could ideally be done? It's like if we put up small water treatment units, like certain of the households like this, with interception points join and they connect to a STP, a small STP, say for 3 or 4 houses, if I'm saying here they are showing you 3 houses. So these 3 houses, whatever wastewater is generated, they are collected and this is treated. And this treated water is discharged into the clean water body from where our water sources come. Or in the water body itself, from where this thing is coming, we put up an STP, we take the dirty water, we channelize it to an STP, treat it and release it to the water body, creating a barrier here so that the water further to this point flows in a clean manner. Can we do these? These are very small units. You don't need to build these STPs in treating million liters per day. It could be as small as few kiloliters per day, few thousand liters per day. Now, what it will do, there could be different situations. An STP which could be constructed under the ground, which is well below. You don't see anything. Something above is a park. Or it could be just above, just at the drain, as I was showing in the previous picture. Or an STP which is above the ground also. In whichever cases, these small STPs and then the treated water goes back to the nearby water body, flowing water body or stagnant water body, or into any other, or its reuse is something actually helping the environment to take up that pollutant pressure. Now, what will ideally be happening is, if we actually do that, so treated water could actually be used, as I was saying, it could be a domestic use, it could be industrial use, it could be community-based use, or even, as I was saying in the previous slide, that the treated water could actually be discharged into a water body, which is actually acting as a source of water supply. All these could be taken up. All these could be thought of. So decentralized wastewater treatment systems and then bringing in the used water concept is what we will discuss today. So where could these water be used? Now, a country like India, which has the largest connectivity or conveyance connectivity through railways, the railway coaches, the bathrooms, the railway platforms, they need to be washed. Why do we need to source the groundwater to do this washing? Simple, if the water, used water or the wastewater is treated to a certain standards, made free of any kind of pathogen, or it is disinfected properly and it is used for washing purposes, it could be used. Or in the power plants as a cooling tower where it needs a lot of water. Why can't this used water or the treated water be used? Or any other industry which uses water for a kind of a non-potable purpose. And the biggest purpose we can do is this horticulture irrigation. I mean, like just a primary and a secondary treatment of the water and a little bit of disinfection with the water. The water would contain enough of plant growth nutrients and that could be used as a horticulture or irrigation purposes. So that what it would do is ultimately reduce the pressure on the groundwater sources or the actual water sources. Water scarcity would reduce, water tension would reduce. So something like that, this could actually be thought of, implemented in certain situations. Now, and ideally, a final picture would look like this, where we would have a drain flowing through our households, by our households, which would be cleaning absolutely clean water or just storm water or rainwater. Groundwater would be clean, which would be giving because there wouldn't be any seepage of the wastewater. It's something which we actually look for, right? We actually read through in books, and that is what we look for today. We seek it. It's a challenge we can't get to see it today nowadays. Now, the same thing, I'm actually trying to say it in a kind of a flow sheet. There are different ways of use water management. One is at the household level, where we put up some best practices of water efficiency, efficient fixtures, certain technologies which would save water, which would give me some sensor-based water dispensing units. Along with that, a baseline uniform plumbing code a country could come up with. As a second step, there are these alternate water conserving methods, be it rainwater harvesting, be it air conditioning, the water that gets condensed. If we can recollect that condensed water, capture the reject. All of you have RO water systems in your drinking water. I mean, every kitchen has it. Now, have you ever seen that for every liter of water that you collect in the jar to drink, the outlet pipe, how many liters of water does it reject out? Can we use that water? That water is not bad. That water can be used. Okay, the liter of water I am taking up from an RO, okay, fine, I use it for my drinking. But then there are other uses in my house which can take up that reject water. Or any other explore options. I mean, I feel bad to say, but yeah, today we are in a position that we need to purchase water. And I don't remember in my childhood when I used to go out with my parents on holidays, we bought water. I'm 47 today. We didn't buy water and drink. There were taps. We used to take the water. But today we don't. We can't. We don't have that what you call strength, mental strength that we can. We actually buy waters. We have made water a commodity. So we can find out different ways of purchasing treated water, selling treated water. And to do that, we need to implement proper used water treatment systems. Once after treatment, we can either give it back to the local aquifer, we can give it back to the local water resource, or we can use it inside or outside our domestic household purposes. All these could be taken up. Just to look at it, where do these, I'm talking of used water, I'm talking of green water, where do these water come from and what is the characteristic? If you remember just a few lectures back, I talked to you about the chemical and the biological parameters based on which we actually determine the quality of water. And when we talk of gray water, if you see the row on top, the bathroom, the laundry, the kitchen, these are some of the sources of gray water. And if you see the numbers, these are the numbers. It is the same characters, biological characters, chemical characters I had spoken of. It is the same characters. It is just that it is much more in a diluted form. If you see the numbers when I spoke about septage, which were about 10 to 20 times higher than the numbers mentioned here. It's just that difference is there, that this is much more dilute. This is much more lesser pollutant containing in terms of certain pollutants, in terms of my biological pollutants, in terms of certain organic pollutants. Inorganics, more or less, they stay the same. Rather, gray water has more of the inorganic content. But then, okay, treatment is much more easier because the content is much more lesser. So again, this is boxed out with the usual solids characters. What are the different kinds of indirect pollutant measures, the nutrients, the microbiological characters, the inorganic characters. As I told you, gray water generally has a higher content of inorganics. So these are some of the inorganics we need to look into. And of course, there are certain of these emerging pollutants that are coming up day by day, every day. whether it is the antimicrobial resistance compounds or the breakdown of antimicrobial products or the carcinogenic products, teratogenic compounds. All these are some of the emerging pollutants that are coming up day by day in water. We need to check the parameters also based on the kind of use or reuse we are planning. Now, I was talking of where could we use this? As I said, within our household and within our house premises, we can use it for plantation, horticulture. If we put up a proper dual plumbing system, we can actually use this same treated water for toilet flushing, floor cleaning, cooling of towers, vehicle cleaning. All these could be taken up. Outside the premises, of course, as I told you, there are certain industrial uses. Irrigation is, of course, there. Street washing is there. Construction purposes, mainly for the curing purposes. Of course, there are certain chemical parameters. If I go back to my previous slide, this component, sulfate, chloride, these are some of the components which we need to be very careful about if we are using it for construction and curing purposes. There are certain standards, limits, which should maintain, otherwise the curing process will go on. Or they could be used discharged into public sewers, into the water bodies. There are certain, same thing I'm trying to say is that the using process specific, we can go for centralized usage of water or the decentralized use of water. All these are there. So what I'm trying to see with this diagram here, which has been actually drawn by one of my colleagues, she tries to say that if we do a kind of reuse of the water in flushing, landscaping, chilling, we actually bring down the pressure of the freshwater source or freshwater demand to a particular building. And that is where we are building in a kind of circularity. This is where we are building in a kind of concept of used water management. It's not that something we are talking new. There are several of these countries like Germany, China, USA, Japan, Australia. If you see, this is a collated table where they have actually different standards for different kinds of uses for used water management. It's not something new we are talking of. It is already practiced. We just need to bring it into our own practices. That is what I want to talk about, emphasize about today. Of course, when you are talking of treated, I'm talking of treated used water, treated water. How do we treat it? So there are certain considerations we need to take when we are going into a technology selection. To what quality I need to treat the sewage? What would be my power requirement, land requirement, capital cost? What would be my O&M cost? What would be, how much of attention the operator would be requiring? That is, how much manual intervention would be there, how much automation could be there, how much reliability on the treated water can I go for, and how much or how much load fluctuations. Someday there would be low loads coming up into the treatment plant, someday there would be high loads coming up into the treatment plant. What should I say, how these load fluctuations would be taken up by that plant. So these are some of the criteria we should keep in mind when we talk of these technology selection of particularly setting up these decentralized wastewater treatment systems. And if you see, if you see the base of the slide, there are certain of these very prominent technologies which are either biological based or biological and mechanical based, whether it is activated sludge process, flow anaerobic sludge blankets, waste stabilization ponds, moving bed biological reactor, sequential batch reactor, membrane bioreactors. And if you see the table above, tries to do a comparison on the goods and bads and how good and how bad this is. I'm not going point by point, just to look into the paucity of time, because this is where our following speakers or the further speakers will actually talk to you about these certain of these technologies and how they have been working on it, design them, implemented them, and what are the benefits they are getting out of it. That is what they would be talking about. So it's not just theory. Today we will be meeting some practitioners and they will be speaking to us. These are some of the same kinds of consideration. If that was on the performance, this was on some of the other parameters we talk of. And of course, to do this, bring into the circular economy of water, use water management, there are certain steps we need to do is collating the existing standards and then making a standard for a particular country or a particular region or a particular ULP anywhere. Devise an action plan, how we can implement these adopted standards. Of course, we need to set up proper monitoring regimes to monitor those technologies, to monitor the outputs of those technologies, and finally, optimize the complete chain of market, right from the treatment to the user, buyer, seller, everybody in the used water management sector. Having said that, I guess you've got a fair idea of what we mean by used water management. I would pull down my slide and I would ask if there are any questions. Here, there are certain questions. May I take the questions? What is the reasonable treatment option available of stream water irrigation canal? Tell us, is any research available on wastewater affects human health? There are several papers right now I can share with you, Nasir Saab, where this research on wastewater and how it affects human health and life expectancy and overall economics of a region. I would share with you in the group, we will share with you several of the literature. There are certain very well-published papers from very impact factor journals like Lancet and all. So we will surely share it with you for you to read them and understand them better. Talking about treatment options, this is what our next phase of talk is I would invite upon first Mr. Ganges Reddy, who works on some nature-based treatment technologies. He will actually drag you through those technologies, and then he will speak about his business model, how he's working out, and how it has impacted in the places he has been working out with the nature-based technologies he's been working for used water management. Over to you, Mr. Ganges.
Good afternoon, sir, and thank you very much for the introduction. And that was very good platform for us to present the next concepts. Can I have the screen sharing enabled? That's good. Good afternoon, everyone. Thank you for the opportunity to present this nature-based solutions to this group here. Looks like we have a very wide, broad.
We have, Mr. Reddy, we have for this course, we have this time more than 82 participants from 11 different countries.
Wow.
So your audience is good. You have an audience of 11 different countries today.
Fantastic. Thank you very much. So can you see my screen?
Yes, absolutely. Perfect.
Okay, so having learned the concept of the used water management requirement and the various options that were available, so now we are walking through this nature-based solutions for used water management. And there are certain technologies within the nature-based solutions that we deploy. So I will share my field experience largely so that it comes to you very clearly that these are the solutions that are working in the field and they can be adopted. The design, of course, requires based on the climatic conditions and in the nature and quality of the wastewater, the design will be different, but otherwise, yeah, these systems can be applied pretty much everywhere. These are typically the known systems that the world has been deploying for used water management. These technologies are mostly, electromechanical conventional systems. Some of them are sequential batch reactors or MBBRs or MBRs, or the classical ASPs, or extended aeration, etc. These are the technologies. They kind of belong to a similar category in terms of treatment. All of us are aware that the wastewater has certain characteristics. The bacteria that is there in the fecal matter or food that joins the water and makes it a wastewater the bacteria survives on the oxygen that is there in the water. So that when the bacteria starts to take away the O from H2O, they create biological oxygen demand on the water. So the BOD levels keep going up based on the organic matter that is present in the water. Similarly, whenever we are using chemicals for our domestic or industrial consumption, like you're using shampoo, soaps, detergents, dishwashing liquids, Harpix for your toilet cleaning, any kinds of chemicals that you're using for cleaning and other purposes are oxidating with the oxygen that is there in the water, and they are taking away the oxygen from the H2O. They are creating demand chemically. So there is a biologically created demand oxygen, there is a chemically created demand on the oxygen in the water, and then they constantly add suspended solids. Typically, the conventional mechanical systems try to provide that oxygen by pumping a ton of air into the water at the bottom of the basins that you can see in the middle of this picture. That you send a kg of air, you get about 20% of oxygen available, out of which about 2 to 3% may be transferred into the water, and the rest of it escapes the ambient air. So this requires heavy amount of machinery to constantly pump the air and then make a thick liquor of the water. And once it uniformly mixes, all the solids become tiny suspended, suspended particles. Then we typically do some coagulants, flocculants, and settle down all the organic matter that is there, that includes certain dead bacteria, live bacteria. And then the supernate water is actually moved away from these basins and for further treatment. So in conventional mechanical systems, we are providing air, and then we are flocculating it or coagulating it. Then we are separating the supernate, and then remains a slurry or a sludge that has to be further treated. This is the method that is used in most of these. In some places you use membranes, some places you don't use membranes, but use other filter mechanisms. Here we are separating the wastewater from the waste. So the sludge consumption is very minimal. The sludge has to be separated. So this adds on some advantages, also some challenges. Now we move on to the challenges that we see with this conventional electromechanical systems. When I say challenges, it doesn't mean that it's a problem with every system. It takes work, and if you are prepared to put in the work, these systems do work. Anywhere you have deployed machines and equipment, they require attention. They will go through these repairs and maintenance. There is a skilled workforce requirement to manage this machinery. And of course, they run on energy all 24 hours. So the energy bills are reasonably high. And the availability of energy also becomes very critical for these systems to run. And like I said, there is sludge that you have to separate and which has to be handled. Of course, it's a wealth in some cases, it's a nuisance in other cases. It depending on what level of sophistication do you have in the design and the technology. And most of the sewage treatment plants, when they expose the water in the tanks to open air, and when you continue to chill them, you find odors, because there are these particles, aerosols out in the air, and whenever ambient air gets in contact and a wind blows over it, it will naturally take all these odors to the surrounding areas. So there are odors, there is noisy and less effective lifespan, because anything that is constantly moving will have a life cycle. So majority of the systems are designed to last for 30 years, but in my experience, I haven't seen systems working that long. Most systems do survive 10 to 15 years. As they age, if they continue to work, they really take a lot of work from you to maintain them, which is a very common experience with our cars or anything that we maintain. So these are some of the challenges that we find with the conventional electromechanical systems. I mean, I'm no way advocating that we don't use conventional mechanical systems, but I'm saying that these are the common challenges. And what are the alternatives? Nature-based solutions. Why nature-based solutions? Would nature-based solutions work? In the past 5 years, I would say the interest on nature-based solutions has gone up, especially post-COVID era. There has been a significant thrust on going towards reducing emissions, reducing GHGs and things like that. So here we are talking, the climate change and STPs. Is there a connection? Do we have to adopt this kind of sewage treatment only for what reasons? Is it for financial reasons? Is it for environmental reasons? Or is it for convenience? So we are talking about climate change as one angle today. We are fighting these cloud bursts everywhere. The floods and droughts are pretty much common part of life these days. And so the reduction of these emissions becomes a very important aspect of our life. As consultants, as practitioners, as advocates, as philosophers, all of us have to focus on something that what we enjoy today is also a responsibility for us to keep to the next generations. Solving a problem today by creating a problem for future is no solution. So it is a surprising fact that IPCC says that the sewage and effluent treatment systems are contributing significantly to the GHG emissions. So it becomes a responsibility for the designers, for the decision makers to choose the right things for the future, for our environment. Majority of the time, we base our decisions on the cost metrics and convenience. And very rarely we look at environmental cost as a stakeholder in this whole equation. So comes the necessity for us to look at sustainability as a prime option for us, environmental sustainability. When you look at the sustainability matrix, we look at economic as the basis majority of the places. There are others also, but largely I've seen people making decisions on economic. We will get into the economics of this a little later also, but environmental sustainability, social acceptability, and economic viability, all these three become very critical in making right decisions for the infrastructure that we are building for our towns, cities, even for rural areas. So when we talk about nature-based solutions, here they are. You can see them live, implemented and functional in different geographical areas under different circumstances, solving different kinds of problems. All these 5 or 6 different units that you see here, they're all set up for different things. One is a residential colony, another is a township, one is a resort, another is a commercial entity, one is a cement factory. In all these places, we have deployed these nature-based solutions which are delivering outstanding results. So the comparison aesthetically, you can see very easily which ones are making sense. But it's not just about aesthetically pleasing or environmentally friendly. How are they functioning? Majority of the systems that have been deployed, well engineered. I will put a big asterisk here that if a system is well designed based on the water quantity and water quality characteristics, the system's nature-based solutions can function for multiple decades. I have seen a system that has been working for more than 6 decades in nature-based solutions. So some of the systems that we built are crossing just about 10 years age. And I've seen many other systems that are touching 25-year-old, across various parts of the world that I'm connected with. So when we go into the details of one of the solutions that we deploy, this is an aerated wetland system, that this mimics the function of the nature. That when you talk about this nature-based solution, the plants that you see have their root system that is not visible to us now, but these roots carry certain kinds of bacterial colonies. Each of the plant is associated with certain bacterial colony. When the waste passes through this root system, they disintegrate the waste, decompose the waste, convert them into food for the plants. So the entire load of these nutrients that are going through the root system are absorbed by the plants for their growth. And some of the nutrients are kept in their shoots. It's not that all the nutrients are absorbed by the plants alone. Plants take some of them for their growth, rest of them they absorb them and they keep them in their shoots. And the bacteria that is at the root system constantly at work 24/7 free of cost. Meaning any water that is coming in, they are typically, if you see this image, you see the gravel. These are all the gravel beds. The bacteria grows on the roots naturally, and then it multiplies. The moment we provide certain micro aeration, the way I have shown, this takes hardly about 20% of the energy that a conventional system would take. But this gives a huge amount of impetus to the bacteria to grow. And this bacteria spreads over all these gravel media that is there. And anytime the water flows in this gravel media, the bacteria that is there, which has formed a biofilm, would scavenge on this waste that is coming and dissolve it and completely convert that, which can be uptaken by the plants. In the process, all the fecal matter, food, all the nutrients are taken up by this bacteria and a combination of the symbiotic association between the plants and the bacteria, and we get the treated water. You can see some of the construction images, how it's built. It's one of the largest systems, almost about 4 MLD, that's 40 lakh liter system that you see on the right side. So this is one of the technologies that, typically the way it is built is you bring the wastewater into a pumping station based on how deep your water pipes are coming. And then you take them into a preliminary collection or equalization tank or a holding tank, or it's also called biodigester. You can feed them in here, retain them for 18 to 24 hours. And then here the sludge is partially consumed and it's activated. And then that water overflows into these wetland basins where further treatment happen. These all things can be constructed in RCC, reinforced cement concrete, or you can use earthen bunds and liners, or you can use some precast panels. Depending on the availability of materials, the budgets available, you can follow different construction methodologies, and you can achieve the same purpose. End of the day, these basins must be leak proof, that we don't let any sewage water go out. You can line them with HDPE liners, or you can do foolproof RCC tanks. And this gravel is typically filled from 1.5 meters to 3 meters. That's a range of depth that you can use. And these plants, there are different kinds of plants available locally based on which country you are from, which geography you belong to. We have identified 21 different species here that do this work. Each species carries different characteristics associated with different bacteria. So as the water gets pumped in once, you don't have to do any more pumping. It goes by gravity from one to another to another. Finally, the treated water can be lifted up. As Rajeshri sir has said, you can use them for flushing. You can use it for gardening. You can use it for agriculture. You can also do it, use it for car washing and floor washing in urban areas. So the system is fairly simple to operate. The complexity is in the design. Once the design is done, implemented, the user will not have any difficulty. They are least complex in their operation and maintenance. They take low energy. Obviously, they reduce the energy consumption, which means that you are lower in the carbon footprint. They are sludge free. Majority of the sludge is consumed by the wetlands and also in the holding tank. Partly, whatever is remaining that is not digested, we can lift it up once in 2 years or 5 years time, based on how much gets accumulated. They are reasonably noise free. They can tackle variable loads. They can give you a superior lifespan of 30 years, 3 decades. And these are very high performing nature-based solutions. The moment I use this word high performing, why do I use that word? Today, the nutrient removal is becoming very prominent need, because the water that we are not using after treatment and releasing into the downstreams in nalas and water bodies or lakes, if they contain nutrients, they further start putrefying the water bodies. So it is becoming very, very important for us to make sure that if we are not completely using the treated water, it is better to remove the nutrients and release into the water bodies. Otherwise, we are causing immediate damage to the water bodies that are around there. So this is the advantage of these green systems. The systems have been engineered since a long time. Earlier, we used to do 5 square meters of wetland for a KL of treatment. Then we started to do certain bacterial colonies in the holding tank that we were able to reduce further. And then now we are doing aerated wetlands that are giving us a very high efficiency at a very lower footprint. Now they can be put into urban spaces. You can see the quality of water, in one of these projects. You can see the cement factory right behind. This is the only green space that the factory has. It looks fantastic, and they get a best quality of water. This water is being taken back into their factory for their process needs. So you can design the system to deliver whatever quality you need. And just for a comparison sake, I'll show you this video very quickly. So this is in a residential setup. It is set up right next to the bedrooms and balconies of an apartment complex. About 215 families live here. So as far as you walk along this garden, I would say garden, because it doesn't really give you a sense of sewage treatment at all. So we call them as wetland gardens. The entire action happens at the root system, which is not visible to the user. So this is how it is. You can see these bedrooms and balconies right there. The kids come around, play here, no orders here, not much of a noise, because we have least machinery there that is added to these wetlands to generate certain low-level aeration. This control panel controls these blowers and all that, so it's very easy to manage. Compared to a conventional system that So this is a conventional example that you would have to require so many things in a conventional system to be able to treat the water. So this is the apples to apple comparison of a nature-based solutions versus a conventional example. The nature-based solutions, of course, will have some limitations that you cannot build very large systems like 20 MLD, 50 MLD, city-wide 100 MLDs. That large-scale systems are not recommended because they require a lot of land and a lot of planning. But otherwise, you can conveniently build these systems up to 10 MLD. So you can start from a 1 KLD, 2 KLD, like even for a household, you can build a system and you can go up to about 1 lakh population, 100,000 population for a town. So you can build them in different modules. There can be built like parks. People won't be able to realize, and they can build them in a ground floor, first floor type model also if you have space constraints. These are some of the use cases: domestic, commercial, industrial, and that we applied of different capacities. And when it comes to the costings, this is in Indian rupees that, you get a similar costing for conventional versus a nature-based solutions. But when it comes to the operation maintenance cost, you're talking about 60 versus 30. If we take that on a life cycle cost, 60 lakhs per annum versus 30 lakhs per annum, I'm just putting the round numbers. The capital cost of 3 crores versus 2.85 is the same number. But when you see this O&M cost, you're talking about a number here, 13.68 versus 6.21. This is a heck lot of savings. So a nature-based solution is delivering you a greater amount of environmental benefits as well as economic benefits, while they are becoming very socially friendly, people-friendly systems. So, and this is when I say green makes absolute business sense. These are not like organic vegetables that on the street you get them for 100 rupees in the in an organic vegetable store, they are sold at 4 times, 5 times. So not everybody can afford this organic so-called vegetables pesticide free. But here in this case, we have reversed it, that the organic natural way is also costing you less. When you look at the environmental impact, the energy saved against a conventional system was this many units per year, and carbon emissions are averted just this straightforward. Sequestration numbers we haven't calculated, but there are significant numbers that will go much, much higher than this emission that we're able to avert. And you created a green cover like this. We have increased the biodiversity index here. Ecosystem restoration has gone from negative to positive. So we contribute to 6 different SDGs directly by adopting nature-based solutions for wastewater treatment or a used water management. So these are some of the projects that are implemented in other places. So, you can use certain advanced solutions to remediate polluted water bodies that are filled with algal blooms or, otherwise water hyacinth, etc., predatory plants. All of these are coming into the water because there are nutrients available. Either sewage is coming in or sewage is seeping in, or the first rains are bringing huge amount of biological solids and organic solids along with the organic content, along with the water in the first rains. And all the deposits continue to give feed to these algal blooms and all that. Eventually, when plants like pistia or water hyacinth, they're not bad plants, but when they grow too much in their quantity, they actually deprive the water of sunlight, and then water starts to become slowly putrefied, and then aquatic life starts to deteriorate, and the water bodies go toxic at some point of time. So before the water bodies go so bad, we have to pay attention and deploy again techniques that go in tandem with. This is one of the water bodies that we resonated from this to this. How did we do this? We followed the simple principles of nature that enable the food web within the water body. That will take care of everything. How do you enable the food web? There are certain engineered principles that we provide, certain enzymes that break down the complex polymers, proteins, lipids, etc., and make them ingestible for the natural bacteria that is there in the water. Once you do that, then the bacteria will start to pick up and start to digest it. And then you provide certain micro aeration, again, very low energy, low cost aeration techniques we follow. And that will give impetus to the bacterial life. And once the bacteria takes over, then the colonies grow and one eats the other eats the other. Finally, small fish eats this one, and then the large fish eats the small fish. That's how you enable the entire food web within a water body. Once the food web is healthy, then your water body can sustain itself, except in cases where you're getting sewage water every day. in which cases we have to design it in a way that it meets the demand of load that is added every day and can bring this equilibrium. In this case, the load is coming every day, still we brought this equilibrium into this water body. We can also deploy certain technologies for flowing wastewaters, what we call nalas in India. These nalas are obnoxious. They're destroying the air conditioning equipment and refrigerator coils, etc., because they have such amount of ammonia coming out. So H2S, etc., gases emanating from these areas. People can't live that easily here. People put up with this. So we can remediate such those things with advanced technologies. Again, we believe in nature that bacteria is already existent. We have to work with the bacteria, add additional bacteria, or make it easy for bacteria to take up the loads. So everything has to be engineered, but go with methods that are low cost, environment friendly, easy to maintain, and those systems that do not need babysitting, so that we can afford to maintain them for decades. That's all I have. Hello.
One is from Mr. Prajwal and one is from Mr. Roshan. They have actually put up two small questions. I know you would love to address them. So I would ask you to take the questions in the chat box and type out the answers while I take on the next speaker.
Absolutely.
Sure. Thank you so much. Thank you so much.
Thank you.
As the next part of our speakers, we would go into, now you have seen the nature-based system. Now, if you have a scarcity, a challenge with land footprint, can we talk of similar kind of treatment systems in a packaged format, modular format? And for that, I would speak about such. I would like to invite Mr. Kamal Tiwari. Are you there, Mr. Kamal Tiwari?
Yes, sir. Good evening. Yes.
Yeah, please take on. He's from Daiki, and where he would talk about some technologies which are mainly kind of biological, electromechanical, but then they are much more packaged, modular. You can take them anywhere. It's kind of a plug and play kind of a thing. Over to you, Mr. Kamal.
Thank you. So, good evening, everyone. My name is Kamal Tiwari. I serve as CEO and director of this Japanese company called Daiki Axis. We are a 65-year-old company in the wastewater sector, and we have got a lot of experience of implementing such technologies and concept in Japan, and now we are already present in many neighboring countries, including Bangladesh, Sri Lanka, Indonesia, Singapore, and few places in Pakistan as well. So we are talking here with a lot of experience and ground learning. When we talk about used water management and we talk about, let's say, how to treat and how to use this water, we need to recognize that water is it's not a static resource which we are dealing with. It is a dynamic resource or a living resource, so to say, because the characteristic, both quality and volume, can keep changing. And similarly, when you make a choice of a technology or concept or anything, the user has to live with that solution for a long period of time. So holistic approach for the whole understanding of this subject, treatment, and how do you deal with that is very important. And what we say in Daiki is basically it is not only just about technology, it is about the approach, technology, how you package the entire, let's say, technology supply to implementation on the ground, and then maintenance of, let's say, the technology, and enabling the user to own the technology. That is all important. And ultimately, the user need to be aware about what he's dealing with. And there has to be transparent, validated, scientific proofs which are available for everybody to see. And there should be no subjectivity about quality. So this, we are coming with a background from Japan. Japan used to face similar or severe pollution or environment-related challenges in 60s and 70s. Japan was the only country in the world which has faced industrial diseases. And then the government of Japan introduced an act called Jokaso Act. Jokaso simply means purification tank. And when they came up with this whole concept, it said that other than, let's say, the wastewater or domestic wastewater, which is getting generated from household or any such application, if it is not being treated by centralized treatment system, it must be dealt by Jokaso only. And why that? Because if it is left for choice of people, then there are, let's say, risks which are for public health, environment, and public asset primarily. So the entire subject was holistically dealt by this act under the Ministry of Environment of Government of Japan, where they introduced and regulated the entire cycle, and I'll explain it to you in later slides how they dealt with that subject. And it has created a big impact since then and now. Japan is able to treat over 98% of their used water, and their environment, you can see, has completely transformed. Japan now is seen as one of the cleanest environment and water environment in the world. And 26% of that treatment is done by Jokaso. So it is very well, let's say, tested system and concept. And Japan in 80s has eliminated waterborne diseases. Many of our developing nations, including India, we face waterborne diseases, and we can't even think of having even a district which is free of waterborne diseases. Japan as a country eliminated that in 1980s. And this is because of holistic approach to the whole subject. And this is what is basically, I am just pulling up a slide from Jokaso Act, which is, in the act, you have defined what is the water quality standard. So there is no subjectivity. Everybody has the same quality to follow. Product manufacturers who will be making Jokaso system have to necessarily pass through a design and manufacturing test, where maybe design regulations and guidelines are given by the government. Manufacturer will provide a product based on that design, which is tested over all seasons, which is practically 1 year of operation at a live site. And based on successful results, then the manufacturer is allowed to get into manufacturing. Similarly, the companies or the individuals who will install such plants have to be, again, go through a licensing and approval system of government, so that they are able to implement technology in an appropriate manner at the site. Then comes the operation and maintenance, that is also regulated. And like I mentioned, even any person, individual of an organization, whether it is engineer or operator, need to pass through a skilling test. And if they are skilled and certified, then only they can touch such system. And similarly for desludging at the municipal level, there is by law, only people who are, let's say, having a license, they only can take the sludge out of systems or from household, and then maybe they are by law regulated how they will deal with this sludge and where they will dispose it of. And of course, then development monitoring by third parties for everything, which is quality, verification, responsibility fixing, everything is defined in the act. And then there are, let's say, different level. It is not just about environment revival. It is a beautiful economic model which they have developed. At different stages, you have opportunity for different people to participate in this whole cycle, from a Jokaso manager who is responsible for managing, from manufacturing company to construction, maintenance, desludging vendor, inspection agencies, and then training and skilling certification agencies. And everything from central government to local municipal level, vendors, users, everybody's responsibility is clearly defined there. So that is basically from which background we are coming into this technology concept. And there is a whole history of wastewater management here, from natural collection pit, which are available across the world. Jokaso, the sanitation history moved to soak pit, septic tank, and then blackwater Jokaso only, which is right now in India, we talk about basically black and gray water segregation. And then now current Jokaso models, which are popular, and what we use in India is combined treatment of black and grey water, so that you don't have to segregate. And just one point I would like to mention here. Normal understanding is that if you segregate grey water from black water, it becomes easier to deal. But technically, it is more difficult to deal with just the grey water, because you remove the organic content from the mixed water, and it becomes difficult for bacteria to maybe survive at that level of organic content. So this is the history, and now I will tell you just the concept. The concept here is you try to treat used water near to the generation source. It could be a household, or it could be, let's say, cluster of houses. So if you look at, let's say, a metro kind of a scenario, which is densely populated, if you install a Jokaso system at the building level, then you can reuse that water here. Or if it is discharging treated water to the central system, then maybe your capacity is enhanced without increasing the central treatment plant capacity. If it is, let's say, a normal town kind of a scenario where the distance between houses is more or density is low, you can install this in combination with the central sewage system. And in village kind of a scenario, which is on the left hand side, where centralized treatment is very inefficient because of long piping and other area and low density, you can just implement Jokaso at the targeted area. That is the solution basket. And you can use it with centralized system in isolation and everything. This is the typical picture of the product. It comes into construction, capsule type and cylinder type. So we have model from 1000 liter per day, 1 KLD to 75 KLD in different, let's say, the construction and combinations. And the entire treatment system is housed inside the tank, which is made inside a factory. And typically, this is the treatment scheme. If you look at, this is normal treatment system, which is starting from the water can be received by gravity. Solid parts are separated. You do first level of sedimentation and settling of SS. Then you pass it through anaerobic contact media chamber, then through MBPR, followed by second level of sedimentation and chlorination for disinfection. And untreated water and sludge is recirculated back to the system in the first chamber, from where you can remove it in a periodic basis, 6 to 8 months period. And if you look at in the whole system, only moving part is basically a air blower, which has two functions. One is to give aeration to MBBR chamber, and second is to create airlift mechanism in the second chamber to circulate the water again inside the system. And the benefit of this is one process, and second we follow Jokaso MBR process, which is for high quality. And if you look at, this is the quality of water, which is at the inlet, we can receive BOD of 300. And we have different models. There is a choice available to user. If you want to use it for gardening, maybe 20 BOD is fine. So you can directly use AI model. And if you are looking at, let's say, a higher treatment, which is BOD less than 10 and also removal of nitrogen and phosphorus, then you can go with second model. And if you are directly looking at BOD reduction to 5 or so, for maybe some reuse case, then you can use Jokaso AIM type, so and so forth for different standard. One point you need to, let's say, recognize that when you look at used water treatment, then in all the countries, you need to follow certain compliances. So you need to be careful about selection of technology so that you are able to meet compliance requirements. And the choice here is you can install these systems underground or over the ground. And like previous speaker said, in case of Jokaso also, you can reutilize the land. Your footprint area on the ground is almost negligible, and area looks neat and clean and beautiful. You can also go for higher capacity plants by adding modules together. That is also possible. In terms of just for understanding purpose, if you look at, let's say, a 10,000 liter per day capacity plant, what you need in terms of area is 2.2 meter of width, 3.6 meter of length, and almost 2 meter of height. And your power requirement is just 200 watt, which is maybe much lesser than a refrigerator. And these are the benefits. You don't need a full-time operator. Energy consumption is much lesser. Installation is quick. It comes from factory, so your execution time at site is very low. Sludge generation is 50% lesser than conventional technology. You only have to deal with sludge in a 6 to 8 months period. The whole system is made for out of FRP, so the life is very long. 30-40 years is what is estimated life. And also the system comes with the peak flow handling, which is mandatory in domestic wastewater, because morning, evening, you get much higher flow than the average flow. So if it is not available, then you have to build that capacity before the system. In case of Jokaso, that is not needed. Because it is concealed system, it is safe, smell free, and noise is less than 48 dB, so it is also noiseless. And all the claims which we are making for Jokaso are certified by government of Japan, and maybe in India also we have third-party certification. Many 20 lakh over systems are already working for Jokaso, and in India, Daiki already have 600 projects working across. And we already have 2 operating factories in India, one in north side and one in Gujarat. And you can use the same technology platform for different use cases based on your inlet requirement and the environment, and you can also configure the solution based on what is the end usage of the treated water. Another big advantage is you can, let's say, gradually increase your capacity based on your requirement. You don't have to install future capacity from the day one, so you can segregate your investment and also the aging of the equipment. And the water quality, if you compare visually, it is very much cleaner water than maybe the conventional treatment systems. And these are few another examples. This is a power plant where instead of maybe having a central treatment system, they went with multiple unit of Jokaso, and the big advantage was power saving network. So if you can look at it, is reduced by almost 90%. This is again a case of treated use water for horticulture, where you are picking up water from drain and then reusing it for horticulture. And many such plants are working in India. This is again maybe for IT park and residential, and you can see that it is in front of IT park, and what you see is manhole and green area. You don't see any equipments lying around. This is similarly a use case where we have installed multiple plants in Nagpur city in India, and where you have water being used for construction and gardening purposes together. You can also use Jokaso with another scheme for fecal sludge treatment. That is also possible. And we have installations in India across from north to south, west to east. And this is the typical picture of how the factory looks like. This is the second factory in north. And for this, we last year also started skill development course for Jokaso operator in India. So the systems are sustained by users. Already the certificate is in line with the certification in Japan. Last year, between the two governments, there was a MOC exchange between Japan and India to cooperate in this area in India. So that's it. Thank you so much. And I am available for any query or questions you might have. Thank you so much.
Thank you so much, Mr. Tiwari. That was such a crisp and clear presentation. Thank you so much. I'm sure our listeners would put up some questions, but of course, as of now, the question I find from Mr. Keshav Info is probably directed to Mr. Kamal Tiwari. If you are there, please try to attend the question.
Okay, should I answer it here or I should?
Yeah, you could take up, but I don't know whether that question is directed to you or not, because just check. I mean, in the chat box, you would understand better.
Yeah. So if I look at this, there is a comment that there is always an inclination by the city government towards sophisticated. Yeah. So if you look at it, is not inclination or anything. The city government ultimately has to comply with certain environment norms. They are supposed to each treatment plant and the treated water which you discharge, whether if you discharge to water body or you reuse for your own consumption, there is a standard which you have to follow of the water quality. So they the way they would like to do it, they want to become safe. So what is normally the mechanized large systems and treatment processes are already used in centralized treatment system. So that becomes natural comfort there. So anybody else providing alternative technology need to convince them more and need to demonstrate it there. So that is the, I think, the thinking.
Thank you. Thank you so much, Mr. As we progress on for the next part of our talk, like we are talking of fecal sludge management for the past, from the time we have started talking of technologies, treatments, etc. Right? And then we have talked about standalone treatment systems like fecal sludge treatment plants, etc. Now, often the question comes to my mind. I mean, if I live in a big city, a question might come to my mind that my city already has a sewage treatment plant. Why do I need actually a fecal sludge treatment plant, standalone fecal sludge treatment plant? As the next part of our session, I would call upon Mr. Praveen Nagaraja from Bosch Institute, where he would actually open up this myth. Like, if I at all need, why do I need a fecal sludge treatment plant? If I do not, if I already have an STP, can I reuse that, or can I use it or convert it to use and treat septage in that same sewage treatment plant? And if I want to do it, how should I think on? What are the step-by-step plans I should do? What should I do? That is what in the next few moments you would be going to get elucidated about. Over to you, Mr. Praveen. Thank you so much.
Thanks, Rajeshri. I hope my screen is visible and I'm audible.
Yeah, absolutely. Both are
perfect. Thank you so much. It's a great pleasure to be here and to meet participants from different parts of the country and even world.
Different countries.
Different countries, yeah, different countries. It's so exciting to share some work that we have done on co-treatment. Yeah, so this is a case, you know, in a country like India, when we started propagating for fecal sludge management, we found that there are quite a number of sewage treatment plants in big cities. So instead of creating an additional investment and additional space for fecal sludge treatment where the ULB has to operate two different type of infrastructure, the question we had is, can we treat fecal sludge in existing sewage treatment plants or sewage treatment plants that are being proposed? So when we went to, when we approached some of these utility boards and cities, the question that, when we said that, we would like to treat, people said that, no, fecal sludge is different, sewage is different, you cannot mix both, it will ruin our system. How can you treat? So those were the kind of concerns that came out. So what we did is we did a thorough analysis of various STPs, and we took pilot STPs, we added fecal sludge systematically, did a long-term study on it, and then came to an understanding that it is pretty much safe if you do it. It is pretty much safe to add fecal sludge into existing sewage treatment plants. So what we have understood from the few years of piloting and learning is basically co-treatment is very simple if carried out in a systematic manner. So what we have tried doing based on this learning is we have tried creating a decision flow chart of how new cities can approach co-treatment. But before we go into that, I would just like to highlight why there is always a scope for co-treatment in our existing STPs. So in India, the design parameter for sewage treatment plants is always 30 years. So we plan for a 30-year horizon for a population. So we estimate population for 30 years from now. We estimate what is the water supply going to be, and based on that, how much wastewater is going to flow in, so on and so forth. So there will always be an excess capacity in the infrastructure that is being created. And this excess capacity, of course, reduces over a period of time. But this capacity can be used for treatment, for treating fecal sludge. Now, in a city, what happens is, anywhere between 20% to, let's say, 80% of the city can be sewered. So all the wastewater from that comes to a STP. But there are pockets and there are fringes of non-sewered areas. So what should happen to that fecal sludge? So that is where we can use this excess capacity of the treatment plant to kind of treat the fecal sludge that comes from the non-sewered areas. And as any plan would progress, so after 30 years, there would be another plan for augmenting the capacity of the treatment plant for the next 30 years. So as the life of the treatment plant progresses, there will always be some additional capacity which we can use for treating fecal sludge. So the concept is very simple. When you look at the design of STP, there are broadly three main parameters that you see to the right that are used for determining what is the capacity of the STP. So one is how much flow that comes in terms of meter cube or million liters per day. So usually STPs are categorized as 2 MLD, 5 MLD, based on how much flow comes in. The second one is how much organic load it can treat, which is usually expressed in how much kilograms of BOD or COD that it can treat in a day. And also the third is how much solids it can treat. Solids can come as total solids, total suspended solids. So these are the broad main three parameters. If you see the top three parameters that designers use for designing any STP, whether it is SBR, MBBR, nature-based system, any STP for that sake. So what we do is we try to use these parameters and determine how much space is, how much extra space is available at the STP, and based on this, we determine how much fecal sludge can be added. So what we do is we compare STP. STP is designed for, let's say, these three parameters, but what is coming inside is a percentage of it. So we compare with what is the characteristic of fecal sludge in that particular city, and then we do some mathematics to determine how much we can add. I will take you through this in the next few slides. So before we decide for co-treatment, what we need to ensure that, let's say, if it's a new STP that's being proposed, what we have found from business models of desludging operators is they would not like to travel anything more than 10 kilometers because they feel that it is economically not viable for them to travel more than 10 kilometers or 30 minutes distance to dispose of the collected fecal sludge. Now, this is based on some research that we have done and some field surveys and interviews we have conducted in India. Of course, this might vary, based on which country you belong to. So you could have a discussion with your desludging operators to determine what is the maximum distance or time that they would travel to dispose. And based on that, we can determine how far the co-treatment facility or the disposal point can be. Similar is for existing STPs, but in existing STPs, we should also ensure that the existing STP has some excess capacity. Let's say it is designed for 10 MLD, but it is currently being operated at, let's say, 5 MLD or 6 MLD. So there is an excess capacity that is available within the STP to take fecal sludge. The other one is the current STP should already, should not have any operational issues, and they should already be, adhering to the current standards. So, for example, if the STP is not adhering to the current standards, there is no point overloading it additionally. So that is just going to ruin the STP. So if this criteria is met for old STPs or new STPs, then we can go ahead and plan for co-treatment. So what we have tried doing is we have simplified the co-treatment. Of course, when I use the word simplify and when I show you this flow chart, it doesn't look that simple. But when you go through it, there are actually only 7 steps. And I will take you through each of the 7 steps. When you go through each step, you'll understand it is very simple, basic planning that can be implemented and anybody could do in any city where there is an opportunity to co-treat. So the first thing is to estimate how much fecal sludge gets generated, right? Now, I'm sure in this course, you might have come across some modules which says how you can estimate fecal sludge for a city based on the kind of population. So there are different methods. There is a US EPA with standard which says around 270 liters of fecal sludge gets generated per annum. Different countries can also have different estimates. So that gives you an indication of in a city that you want to, for a city or for a geographical area where you want to get the fecal sludge from, how much fecal sludge is generated. The second most important thing is to understand the characteristic of fecal sludge, because that will determine that will also determine what is the organic load you're going to insert or put inside the existing treatment plant. So we need to collect samples, representative samples as much as possible from different parts of the city, analyze it for parameters that are mentioned in this table, and get a range of get a range that this is the minimum, this is the maximum amount of BOD, total solids, that we foresee in our city. So based on that, you can go to the next step of designing. Yeah, I think there's some.
Afa madam, आपने अपनी click to silence करें.
Thank you. Yeah, so the step 2 is to identify which STP or sewage pumping station that you can dispose of the fecal sludge. So as you see in the photographs, they have identified certain disposal points. Now the disposal point can be the treatment plant itself, or it can be a pumping station which is linked to the treatment plant, so that you don't have to travel all the way to the treatment plant to dispose. And now we have, based on our research, we have defined certain criteria that must be met. So these criteria I've also mentioned before, that is basically the travel time and whether there is access to that particular disposal point, and also in terms of capacity. So is there an excess capacity that is available at the disposal point to carry the sludge or to treat the sludge? So once you identify the STP or the SPS for disposal, what we need to do is we need to assess, we need to do a little bit of technical assessment of the STP. So when I say technical assessment, we need to compare what is the actual flow. So let us say it is designed for 10 MLD. We need to see how much is a flow rate that is actually coming in right now on an average per day basis for the last 3 months or last 1 year. So it can be like, let's say 4 MLD or 5 MLD. So that shows that there is a gap, an additional gap of 5 MLD. And then we can also find out what is the treatment efficiency. So when I say treatment efficiency, it means that is the output parameters meeting the standards that are prescribed. Then accessibility, can a truck come to the treatment plant? Does it have an all-weather road? Is there a land inside the treatment plant just in case we need to set up a tank or a screening chamber or any additional infrastructure? Is there a space within the treatment plant? And since fecal sludge has a lot of solids, STP also have, STPs by themselves have mechanism to treat solids. So they can have anaerobic digesters, they can have solid liquid separators such as centrifuge, drying bed, so on and so forth. So they need to have a system for solid treatment. Only then we can add additional solids. So this is the basic requirement that that is required at the STP. So we need to go there and collect this data. And at a sewage pumping station, we need to see how much is the actual flow rate, whether the pumping is already at 100%. So if the pumping is 100%, we cannot add additional flow. And in case we need to set up like a screening chamber or a holding tank, is there space availability at the pumping station? So if we are able to capture this kind of details, we can go to step 4. So before we go to step 4, I just want to introduce that there are 2 ways how we can co-treat. One is fecal sludge can be directly mixed with sewage and it can be treated at the STP, just like how sewage is treated. Now this option, the option that you see to the left, is recommended when the quantity of fecal sludge is very less. When I say less, let's say it is 2 truckloads or less, 2 or 3 truckloads, less than 2 or 3 truckloads per day. Now, if the quantity of fecal sludge is more, and if you're designing something new, then it is always better we do a solid liquid separation method, the one to the right. So what it says is, you bring the fecal sludge, instead of directly adding it into sewage, we kind of separate the solid and the liquid. And the liquid goes along with sewage into the STP, while the solids go to the solid treatment part of the STP. So this is the second method, which is the one to your right, is much better to control, much better to monitor, and will have less impact on the STP. But of course, the disadvantage is you need to create an additional infrastructure, which is that solid liquid separation unit at the STP. Now, step 4 is basically, so let's say once we have determined how much is the extra capacity that is there at the STP, we have determined that 5 MLD is the, out of 10 MLD, 5 MLD is coming. So what do we do next? So there are 2 ways. Like I said, we have determined that there is a hydraulic gap. So there is an extra space hydraulically. We need to also now determine how much extra space is there from an organic and from a solid point of view. So what we do is we calculate what is the design, how much kg BOD can the STP treat. So this is as per design, and how much kg BOD it is currently treating. So that will give us an extra gap. That is how much it can treat, the space that is there for additional treatment. Similarly, we do the same exercise with solids. How much total suspended solid can the STP treat compared to how much is currently inflowing. So based on this gap, then we compare, and whichever is the least, we take that, and then we use that for estimating how much fecal sludge can be loaded. So the formula is very simple. If we know, let us say, X 100 kg BOD per day is the additional capacity that can be used for fecal sludge. We would have done sampling of our fecal sludge. We will know what is the total solids or BOD in our fecal sludge. So if we divide these two, it will give us how much fecal sludge can be added. So it is just a simple arithmetic division based on which we can calculate how much fecal sludge can be added. And if we do it for BOD separately and suspended solid separately, we will get to know which is the lowest value, and we can take the lowest value for as a safer side, so that STP is not overloaded in the other parameter. So once that is done, we have kind of done calculations to identify how much quantity of fecal sludge can be added. We need to see what is the additional infrastructure that needs to be built. So let us say if we are planning to dispose it off at a sewage pumping station, we need to have some mechanism to remove the solid waste that is coming through fecal sludge. So it can be plastic bags, fabric, fiber. So because it might affect the pump that is there. So some kind of screening arrangement, and if possible, a buffer tank, because disposing all the fecal sludge at one point in time might change the characteristics, at that particular instance. So it is always better that we store fecal sludge and dose it systematically or continuously over an elongated period. Similarly, at an STP, same thing. If you're directly disposing at an STP, it is always recommended we have a screening chamber. We have some kind of control mechanism to ensure that the flow is not instantaneous. And if you are going for the solid liquid separation system, we need to have some kind of mechanism such as a thickening tank or a screw press, volute press. So there are different mechanisms that are there which can be used for this purpose. So once that is done, so we have identified how much can be treated, what infrastructure. Let us say we are creating that infrastructure. Parallelly, we should also check that, let's say if the STP is already operational and there is a party or a contractor who's engaged to operate it, they should be trained in how they can manage this additional load that is coming in. So they should not feel that, okay, this is not something that, we do not know what is the characteristic of fecal sludge. It might upset our STP. So we should take them into confidence. We should be able to explain it to them that this is not going to upset, and what are the additional monitoring mechanisms that they need to have in place. We need to also brainstorm on troubleshooting mechanisms. So let's say if something goes wrong because of addition of fecal sludge, what can go wrong and what should be the recourse action. So all this is something that we can prepare the operator for. And of course, we need to do some basic testing so that, we test it for, let's say, a period of 1 month, just to check that the system is not getting upset and so on and so forth. So like I said, the last step is about, the change management protocol and operation control. So how do you convince the contractor and what kind of systems you would put in place that contractor or the operator of the STP is prepared for this additional fecal sludge that is getting loaded. And it is also better that since, like I said, the STP, the capacity of the STP, the buffer capacity of the STP will always keep reducing as more and more households get connected to the sewer network. And if more water is also getting consumed, or during rainy seasons, there can be additional hydraulic load on the STP. So there are many variables in a STP operation. So it is always better that these variables are continuously monitored. And if there is any change in the variable, there should be a plan in the sense, let's say, if the hydraulic load reduces, then the fecal sludge that should be loaded into the system should also be proportionately reduced. So this kind of plan needs to be developed, and the operator needs to be trained or informed about it. And in few countries, they have stringent laws on nutrients such as nitrogen and phosphorus. So the nitrogen and phosphorus values in fecal sludge are sometimes considerably high. So we should also monitor what effect this might have in the outlet of the STP. So so based on all of this, there are a lot of do's and don'ts that we have identified from our research. But you can read about it from my slides. But one key thing that I would like to bring to your notice is whenever co-treatment is very simple. It can be done in any STP which has buffer capacity, but that does not mean from tomorrow onwards you can start co-treatment. Co-treatment has to be approached scientifically. We need to understand the STP very well so that we will not upset the existing STP by adding fecal sludge. So this is some do's and don'ts. And whatever I spoke now is available in these 2 books that are there online. I have also linked, I've also put in the links for these books. So there is a manual for co-treatment planning and design. So whatever slides that you have seen before, the flow chart and all of it, it is available in this manual. So if you want to implement co-treatment, you can just take a printout of this manual and start filling it. By the end of this 40-page book, you will have a very clear plan of how to do co-treatment. The other book is about, if you want to study more about co-treatment, you can refer to the book by Durai Narayana. And these are very rich resources that you can have, that you can make use of. So with that, I'll just open the floor for any questions or suggestions. Yeah.
Thank you. Thank you so much, Praveen. That was awesome. Even I got a lot of recapitulations of what's to be done. Anyways, participants, I mean, if you have any questions for Mr. Praveen, you can always take up. Mr. Mohammed, the comparison of the OPEX is something we'll do at a later part of one of our sessions. Let's keep it on hold. We will do it. Other than that, Praveen, I guess a bit on the heavy for our participants today. So what I would suggest is stay on with us in the sense we would take the participants' queries, questions through the learning management system as well as in the WhatsApp group. They often do post later on. And we will take the questions. We'll go back to you and collect the answers from you and then again share it with our participants. So as of today, let us conclude the session. Thank you, Praveen. Thank you, Mr. Ganges. Thank you, Mr. Kamal, for joining us and sharing your experiences and everything with us. Yeah, Prajwal, you have a question. Yes, Praveen, are you there?
Yeah. Yes. So we need to compare all the 3: hydraulic load, solid load, and the organic load, and whichever is the least. So the value of fecal sludge that can be added, which is the least, or whichever is a bottleneck, or the limiting value. So we take that, and then based on that, we estimate how much fecal sludge to be added. Thank you.
Thank you so much.